Hey, this is Presh Talwalkar. Can you find the total area of the red spots? The diagram involves a rectangle with dimensions 10 and 20. The rectangle has one of its diagonals connected. Inside the rectangle are two circles of equal size, which are tangent to each other and tangent to the rectangle. If you can solve this problem, then try this much harder variation. This was supposedly asked to 6th graders in China. Can you now find the total area of the red spots? Give these problems a try, and when you're ready, keep watching the video for the solution. We'll get started on the first problem. We'll solve for the area of the red regions by subtraction. We'll take the area of this triangle, and then we'll subtract out different portions of the circles. So we can set up a formula that the area of the red regions is equal to the area of this right triangle minus the area of each of these pieces from the different circles. Now it looks like these two pieces actually join to form one circle. You can notice this by symmetry, and I will illustrate it by putting these two pieces together. We now solve for the area of each piece. The area of a right triangle is its base times its height divided by 2. The area of a circle is pi times r squared. The right triangle has a base of 20 and a height of 10. The circle has a radius which is equal to half the height of the rectangle, and its radius is equal to 5. So the circle has an area of pi times 5 squared. This means the area of the red regions is equal to 100 minus 25 pi, or approximately 21.46. Now let's tackle the second part of the problem. We know the area of the red regions as illustrated is 100 minus 25 pi. The second part says, what would happen if you remove this region from the lower left-hand corner? So we can solve for the red regions by solving for the area of this particular piece. To do that, we'll consider a simplified diagram. We'll just consider one of the circles, and it'll be inside of a square with side length 10. We can again solve this by subtraction. We consider this right triangle. We're going to remove this portion from the lower right-hand corner, and then we're going to remove this portion of the circle. And what remains is the area of the lower left-hand corner. So we'll set up our formula that the area we want is equal to the area of the triangle minus the area of this piece in the lower right hand corner minus this piece of the circle. The area of the right triangle is its base times its height divided by 2. This right triangle has a height of 5, so its area will be 10 times 5 divided by 2. What about the piece in the lower right hand corner? We can solve this by subtraction. We'll consider 1/4 of the square. This square has a side length of 5. We then subtract out 1/4 of the circle. So we can solve for this piece by taking 1/4 of the square and subtracting out 1/4 of the circle. This square has a side length of 5, so its area is 25. The circle has a radius of 5, so 1/4 of the circle is pi times 5 squared divided by 4. So we solve for this portion as 25 times 1 minus pi over 4. So we just have one more piece to solve for. This is the most complicated part. We'll again consider it by subtraction. We'll consider this sector of the circle. We'll then remove out this isosceles triangle, and that'll leave us the area of the piece we want. So we can again set up a formula that the region we want is equal to the area of a sector of the circle minus the area of this isosceles triangle. In order to calculate these areas, we're going to have to use formulas for these particular shapes. If we have a circle with a radius of r and a sector having an angle alpha, and this is in radians, then the area of the sector is equal to r squared times alpha divided by 2. For a triangle with side lengths AB and an angle in between them of beta, its area is equal to A times B times the sine of beta divided by 2. So we now need to consider what are the angles involved and what are the lengths involved in these formulas. Well, the circle has a radius which is 1/2 of the square, which has a length of 10. So the radius is 5, and the radius is 5 over here too. This is also the other side of the triangle. So we have an isosceles triangle. If we consider the right triangle from the lower left-hand corner and say this has an angle of theta, the radius of the circle will be parallel to the side of the rectangle. So its corresponding angle over here will also be theta. The other side of this triangle, we have an isosceles triangle, so it will also have an angle theta. This means the central angle of this sector will be pi minus 2 theta, because the angles in a triangle add up to pi radians. So we can now substitute in these dimensions into our formulas. We can simplify the formula for sine of pi minus 2 theta, because sine of pi minus 2 theta is equal to sine of 2 theta. Sine of pi minus any angle is equal to sine of that angle. So now we need to consider, what is this angle theta? Well, in our original triangle, it has a height of 5 and a base of 10. So we can use trigonometry to say that the angle theta is equal to the inverse tangent of 5 over 10, which is the inverse tangent of 1/2. So we can substitute that in, and we'll simplify our formula for the area of the sector. Now for the area of the isosceles triangle, we can use the double angle formula for sine of 2 theta, and simplify that a bit. And now we need to solve for the sine of theta and the cosine of theta. Well, in this right triangle, we have one side length 10 and a height of 5. So we know that its diagonal can be solved by the Pythagorean theorem. So we have 10 squared, which is 100, plus 5 squared, which is 25. So that means the square root of these the sum of these is equal to the length of the hypotenuse. So the hypotenuse is equal to the square root of 125. So we can solve for the sine of theta as 5 divided by the square root of 125, and the cosine of theta is equal to 10 divided by the square root of 125. So substituting that in and simplifying, we end up with the area of this isosceles triangle is equal to 10. And now we have a formula for the region of the circle that we want. It's 25 pi over 2 minus 25, the inverse tangent of 1/2 minus 10. So we have all the different areas of the pieces we want, and we can simplify this formula to get the area of the lower left-hand corner is equal to 10 minus 25 pi over 4 plus 25 times the inverse tangent of 1/2. So we'll put this all together. This is approximately 1.956. So now we're going to put this all together, and we're going to calculate the area of the red regions. So as illustrated, the red regions are 100 minus 25 pi. In our second problem, we want to remove this one piece in the lower left-hand corner, which we just solved for. So we can substitute that in our formula and then simplify to get the area of these red regions is 90 minus 18.75 pi minus 25 times the inverse tangent of 1/2. And this is approximately 19.504. Did you figure this out? Thanks for watching this video. Please subscribe to my channel. I make videos on math and game theory. You can catch me on my blog, Mind Your Decisions, which you can follow on Facebook, Google+, and Patreon. You can catch me on social media at Presh Talwalker. And if you like this video, please check out my books. There are links in the video description.